Okay, welcome everybody to this course. I really have the pleasure. Let me see. Let's put full screen here. It's really a pleasure for me always to share knowledge, and whatever I know, I love to share with my colleagues. And I really believe in synergy, as everybody has different skills, and together I think that we can make the difference. Then my goal in this workshop is to introduce you to the world of the population PK/PD without using too much mathematics and statistics that I know very well, but I don't think that's really the goal here. The goal here is to work on the intuition, to explain the concept in such a way that you will be able to understand the concepts, and then to shift to the next gear, which is how to implement the concept within the software framework. And here it will be the R and LME. Then the only things that I assume that you are familiar with, it's just the basic concept of pharmacokinetic and pharmacodynamic. For pharmacokinetic, for example, to understand what is a clearance. From a modeling perspective, what is a one compartment model, because that's what we are going to use as the reference. And other than that, that's it. Then we are going to talk. We are going to talk about two different worlds. The world of the parameters, because you have a model, and the response is the concentration, and then the model depends on parameters. For example, for the one compartment model, the two parameters are clearance and volume, if it's an IV. Then I'm going to take as a template parameter the clearance. We are going to build all the concepts that are needed to understand and apply the population approach. When we are done with the word of the parameters, we are going to talk about the second word, which is the word of the response, because the response depends on the parameter, but what we observe is the response and not the parameter. We estimate the parameter. Once we estimate the parameter, we can predict the response. If we have data single dose, we can predict multiple dose, etc. And that's all the idea. And let's just talk now about why do we need to use the population approach. You know, me as a simple guy, I could say, let's just take data from 20 individuals. Let's just take each individual differently, separately. Let's just take the data for one individual, each at a time. And let's just try to estimate the parameter of the model for each individual. And once I have the parameter for each individual, I'm just going to summarize, find the average and the variance, which quantify the variability about the, across the population, and I'm done. And I have everything that I need. Then why in reality, in practice, it doesn't work? That's basically the main question, why basically it doesn't work. I'm just trying to go to the next slide. Okay. Okay. In reality, there are many reasons why it doesn't work. The first reason is that real data usually are not really rich. And what does it mean rich? It means that we do not have a lot of observation per patient. If we have 1,000 observations per patient, we could take each patient and we would be, and it's not always the case, but most likely we'd be able to fit a simple model to the data because we would have a lot of information. I'll give you a simple example. Suppose you have a drug that is absorbed. Then you have an absorption phase and you have an elimination phase. If you have a lot of data during the absorption phase, a lot of data during the elimination phase, and also a lot of data during the distribution phase, which means that the drug is going from the central compartment to, let's say, tissue and back to the plasma compartment, then I would be able most likely to estimate the parameters. In practice, we don't have that, especially in phase 2 and phase 3. Then because the data are sparse, it's not good enough to just use the individual approach, and we need to use the population approach. When we are talking about the population approach, we are interested first in the population characteristics. In other words, if I have 20 patients, my first goal is to tell you, this population, the drug for the population behave a certain way. For example, the average clearance is equal to 5 milliliters per hour, and I have, let's say, 30% variability across the population. And then I'm giving you the same information for the volume. And then once I'm giving you the information for the volume and for the clearance, I can give you the information about the concentration time profile across the population, which is what I need, because most of the time, if, for example, I know from previous study that I need all the patients to be within a certain therapeutic range, I could use simulation to know what should be the dose to make sure that at least 90% of the population will be in the range that I want. The problem is that the range I want, I can define, but the range that I'm covering, I don't know if I'm not doing simulation. And all the goal is to take the data, to understand, to characterize my population in terms of their parameters, and then to answer to the question, what dose should I use to have 90% of the patient of the population within a specific range. In the population approach, again, we are especially interested in the population characteristics. Now, what is the hypothesis? What is the basic assumption that we are using that is required to use the population? Because you cannot always use the population. The population approach, something very important, is that there's something in common among the individual, which is the central tendency. In other words, everybody share the same average. And again, it's assuming that I don't have covariate. I will talk about covariate later on. Then and what's happening, for example, if I'm talking about the clearance, then basically, if the average clearance is 5 milliliters per hour, and again, the value are not really important here, it's not really real value, then what will happen if I was able to take 1,000 patients, then if I was able to take 1,000 patients, I would see that some patients have a value less than 5, some patients have a value larger than 5, and at the end I would see that I will get the distribution. In our case, it will be what is called the log normal distribution. We are going to talk about that. But if, for example, we have a mixed population and we don't know where the mixture is coming from, in other words, that I see, let's say, 50% of the patient has bounce around a mean of 5, and 50% have the clearance bouncing around 20. That's called a mixture. If we don't know where it's coming, the mixture, in other words, that we don't know what's the covariate that explains the mixture, then we cannot use the population approach. Or you have to use a special technique called mixture for population. And we're not going to talk about that. Then it's very important to understand that we have this basic assumption. Now, the population, then you could say, yes, okay, but what do we earn by using the population approach? And let me give you just a simple example. Suppose that one patient, for some reason, has no information during the absorption phase. In other words, you took samples only when the drug starts to be eliminated. Obviously, if I had only that individual, I have no clue what is this absorption rate because I don't have data there. Then when you don't have information about the specific patient parameter like absorption, the program automatically is going to borrow the information from the neighbors for all the patients from which you have information about the absorptions. Obviously, mathematically, everything is set up, and I'm not going to enter into that. The idea is that because we believe that if a patient don't have information about the absorption, other patient has information about the absorption, or if a patient don't have information about the elimination because he dropped out before, because his drug, it's a drug level, his drug basically had the time to be eliminated, then other patient will have information about the elimination. At the end of the day, you will be able to estimate the population characteristics, even when you have sparse data, or some patients have very, very small number of observations. And that's basically the basic idea. Now, when we are talking about the parameter space, we need to understand some concepts that are very important. And I'm going to spend some time about this concept, because without understanding this concept, you will not be able to pick up the population approach. Then, what are the concepts? We have the concept that I call fixed effect. random effect. Within the random effects, we have two kinds of random effects we are going to talk about. And one is called inter-individual variability, and the other is called inter-occasion variability. And then we have the concept of the covariate analysis. Then let's just start with fixed effect. The fixed effect has two words, fix and effect. Then what does that mean? Now, every time that I have an equation, I'm going to put it in red, and I'm going to explain what does that mean. And again, I'm talking about a fixed effect. Now, what I want to write here, it's just the generic or the general equation for the clearance of any individual. And you can see that the clearance for any individual is the product of two terms. What one called the TVCL, which is the typical clearance. That's basically, in fact, the fixed effect, multiplied by exponent NCL, and NCL is called the random effect. And again, I'm going to explain everything. Don't be worried about that. Then, what is basically, in other words, suppose that the fixed effect, which is when we don't have covariate, it is basically, if you want, the average. Okay, CL, it's the individual clearance. TVCL is the typical value for the clearance, if you want, average or median. And NCL, it's a sample from a distribution that it's normally distributed, that has a mean of 0, and a variance that quantifies the population variability that we call W square CL. And again, we are going to talk about that later on. For example, suppose that the average clearance is 5, and 5 is not picked from a distribution. Because 5 is not picked from a distribution and it's called the typical clearance, it is called the fixed effect. Because a fixed effect is not sampled from a distribution. Contrarily, NCL is picked from a distribution that has a mean of 0 and a variance of W square CL, and that's why it's called a random effect. For example, because everybody has in common the mean, when we don't talk about covariate, then the mean for everybody is 5, and if NCL equal 0.1, then that patient has a clearance of 5 multiplied by exponent 0.1. If another patient has an NCL of -3, then his clearance will be 5 multiplied by exponent -3. Now you are going to ask me, why did I put this exponent? And let's just talk about that now. Suppose that I have a mean, TVCL, of 50 milliliter per hour, and the variance equals 5. Now, we can predict the average time profile for the population when assuming the variance of the population is 0. In other words, if I put 0 here for NCL, exponent 0 is 1, and then I'm getting the average. Then basically, eta, what I call NCL, basically, it's called also for other software eta, or if you want the random effect for the clearance, if it's 0, then I'm going back to the average clearance. Now, if now I want to simulate many patients using NCL, which is a sample from a normal distribution with a mean of 0 and a variance of 5, I can simulate many random effects, NCL. NCL is the random effect, and we will estimate its variance as well as NCL itself given the observed data. That's what we are going to do when we are going to do the fit. But if I want to simulate many patients, I can do that. I can simulate, let's say, 10,000 patients. I know TVCL equal 5. I know that NCL is a sample from a distribution that's normally distributed with a mean of 0 and a variance of 5. Then I can get 10,000 value for NCL. Each value that I'm getting, I'm putting this in the exponent domain. And then when I'm getting that, you can see that I'm getting what is called the log normal distribution. Now you should ask me, okay, why did I use the exponent? The exponent is to make sure that the clearance, which is a PK parameter, will stay always positive. And again, because we know that most of the PK parameter, if not all the PK parameter, must be positive, we always make the assumption that at the end, if the random effect is normally distributed, the fact that we use exponent here make this original random effect that was normally distributed makes the structural parameter clearance log normally distributed, and that's why you get basically this picture. And that's basically explain both the fixed effect and the random effect. What you can see here, it's basically the random effect when I simulate 10,000 value for NCL. You can see that I'm getting a normal distribution. But when I'm using the equation for the clearance, the normal distribution, that is the distribution for the random effect, convert into a log normal distribution for the structural parameter that it's called CL. Then again, NCL is always normally distributed. To make it exponent, transform the normal distribution into log normal distribution. To multiply by TVCL will make the distribution center basically around that mean value. This, what you can see about the zero, is basically what I'm getting when I do multiply everything by that clearance. Then again, what did we learn so far? Fixed effect define the central tendency for the structural parameter. Individual random effects are always normally distributed, while the inter-individual variability for the structural parameter can be of any distribution shape depending on the transformation used. We use so far only one transformation, which is using the exponent domain, but there are other transformations that we can use, okay? Then I would like to stop here once again just to see one of the mentors, if for some reason there are some questions before we go to the next step, which is defining what's the inter-occasion variability. I just want to know if some people have some questions. Then if one of the mentors just can tell me that there's no question, or I can continue, whatever. I guess there are no questions, which is either good sign or bad sign, and I hope I'm a positive guy, then I will assume that it's a good sign. Then again, what I explained you, is that we have a fixed effect, and a fixed effect is not a sample from a distribution. It's a value that basically, if I knew that value, I could tell you what's the average behavior of my population. And we have the random effect that quantify the inter-individual variability, which means how patients are different one from the other. Remember, how patients are different from one from the other. Now we are going to talk about another concept. Once again, something is going wrong here. Okay, I have some problem with my computer, I don't know why. Then again, inter-individual variability quantify the variability between individuals. Now, I'm pretty sure that you are all familiar with crossover studies. In crossover study, in the design of the study, what will happen is that you take the same patient and you give one formulation, then two, and you wait washing period, let's say for 2 weeks, and again, you give either another formulation or even the same drug, same formulation. Sometimes you repeat basically the blood sample collection 2 weeks later and then 4 weeks later. Every time that you have a new collection of samples, we can call this an occasion. Now, what can happen is that if on week 0, for example, the clearance is 5 for the patient, randomly, what can happen is that 2 weeks later, then the clearance shifts a little bit down, for example. Instead of 5, it's 4. Then 2 weeks later, it's 6. Then again, 2 weeks later, it's 3. Then 2 weeks later, it's 6. What can happen is that from week to week, every time that you collect samples, suddenly and suppose that you collect a full profile, suddenly you see that the clearance bounce randomly around the mean value, which was 5. Then, unlike what we talked about just before, where I told you that the inter-individual variability quantify difference between individuals of the parameters. We can have also inter-occasion variability that quantify the variability of a parameter from occasion to occasion, or if you want, within the same patient. We use inter-occasion when you have trials like crossover study, or you have a multiple dose and you collect data in the first dose, and then at steady state, then sometimes you can have some parameter that randomly fluctuate from occasion to occasion. Then let me give you an example, and I just say example helps a lot. And suppose that I have patient 0, patient 1, and you can see patient 0, patient 1, and patient 2. And again, it's a crossover study, and you have 3 occasions. And let's just look again visually, because visually sometimes it helps a lot. You can see here that an occasion 1, an occasion 2, and an occasion 3, you can see that the clearance look the same. Again, what I mean is that if you look at the slope in the log domain and they start at the same value, which means that they have the same volume, and then here basically you can see that the slope is really the same, which means that the elimination rate is the same, and then if you want, the clearance is the same. Okay? Now, if you look here, everybody starts at the same spot, which means that they have the same volume of distribution. But what you can see here, what you can see here is that the clearance here is basically larger than the clearance here, and then basically you can see here it's faster, and here it looks quite the same, and then here is basically slower. You have a slower clearance. If I'm looking at the next patient, you can see that the pattern changed completely randomly. Now we have slow clearance, very large clearance, and large clearance. If you see many patients and you see that there is no definitive trend, and what is a trend? If, for example, you would see every time I see that the clearance on the first occasion is slower than the clearance on the second occasion, and the clearance on the second occasion is lower than the clearance on the third occasion. That would be basically a systematic trend. If you don't have a systematic trend and you see that basically the clearance bounce randomly around its earned value for each individual, this is called inter-occasion variability. And again, if, for example, this value was 5, then this is 5, and this is 5, and this may be 6, and this may be 6, but this is 3, and this one for patient 2 would be, let's say, 4, and this should be 8, and should be 8. Then randomly, if it's happening, then we call this inter-occasion variability. Now, how do we are going to model that? For the meantime, the only things that we saw is basically the quantification of the inter-individual variability. How patients are different from the other. Now, within the same patient, and clearance is the clearance for one individual, I need now to quantify another random effect, which is the inter-occasion variability. And how we are going to do that? Again, let me suppose that I was able to do 1,000 trials under the same condition, or if you want even more, suppose that every week I would have rich data, and let's say 1,000 times, and the average clearance is 5, and then now every time randomly from occasion to occasion, the clearance changes. Sometimes it's 4, 4.5, 5, 5.5, 6, etc. I have 1,000 value. It defines a distribution that will be centered around the 5. In other words, if the 5 is already here, TB cell is here, it will be centered around 0. Okay, exponent 0 is 1. Okay, and then it will fluctuate from occasion to occasion. I have 1,000 value. It defines a distribution that has a mean of 0 because the 5 is already here, and that will have a certain variance. And now I want to simulate that. Then we assume that there's a distribution called inter-occasional distribution that has a mean of 0 and a variance that we are going to estimate. NCLX1 is a sample from that distribution. Let me give you an example. Suppose that TVC equal 5. Let's say that's the mean. And suppose that NCL equals 0 just for simplicity. Then basically, we are going to have from occasion to occasion, the clearance fluctuating around 5. Now, if NCLX1 equal minus 0.1, an occasion 1, that's why I'm putting occasion equal 1, which is called an index that take the value of 1 if the occasion value equal 1. Then on the first occasion, on the first week, for example, then this is equal 1, but this is equal to 0, and 0 then doesn't count because exponent 0 is 1. Then let's talk about the first week. Occasion equal 1, then occasion equal 1 is 1. And suppose that NCLX1 equal, let's say, minus 1. Then it means that that patient has a clearance of 5 multiplied by exponent minus 1 on the first week, because I assume that NCL equals 0. Suppose that on occasion 2 and week 2, let's say it's every week I'm getting samples. Suppose that NLX2 equal 1 instead of minus 1. Then what will happen in week 2 is his clearance will be 5 multiplied by exponent 1. And suppose that on occasion 3 it's 0.5. Then on the third week, the clearance will be equal to 5 multiplied by exponent 0.5. If I would continue that forever, you would see that basically the random effect, the sample from that distribution, will basically fluctuate around 0 with a certain variance, which at the end will be the variance of the inter-occasional variability, random effect, the inter-occasional random effect. Remember one thing very important. NCLX1 is a sample from a distribution, and W is defined as the variance of that distribution. I want to show you again, you can see the NCL is a sample from a distribution, but that change from individual to individual, okay? And the variance, we call it W squared CL. Same thing for the inter-occasional variability. NCLX1 is a sample from a distribution that has a mean of 0 and a variance that the program is going to estimate, okay? And is going to change from occasion to occasion within the same individual. Then when I multiply CL, TVCL by exponent NCL, I quantify the inter-individual variability, which means how patients are different one from the other. When then I multiply on each occasion by the random effect NCLX1, NCLX2, and NCLX3, I'm getting the fluctuation of the clearance from week to week. Okay? And here again, I explain exactly what I told you. Suppose that TV cell is equal 1.5, then random effect NCL is 0, 1, and minus 1 for patient 0, 1, and 2. Then if we do not account for the inter-occasion component, we get the following clearance. If we have no fluctuation from period to period, then you just look at the inter-individual component, and then you get for each patient basically their clearance. Now, if you have random fluctuation, which is written here, you can see NCLX1, NCLX2, NCLX3, patient 0, 1, 2, you can plug this value into the equation, and you are going to, and I would like you to try at home, and you are able to define what would be the clearance for each individual, which is quantified by the NCL, but also on the 3 different occasions, 1, 2, and 3, week 1, week 2, and week 3. The program is going to estimate both the variance of both the between subjectivity variability component as well as the inter-occasional random effect. The variance, and also for each patient, what are the individual random effects. And remember that the variance quantifies the population variability, either between subject or within subject, and the NCL and what I call the NCLX1 and NCLX2 and NCLX3 basically are a sample from that inter-occasional distribution that the program is going to estimate. The idea is that the program, and RNLME apparently is going to give you all that, at the end of the day, when you're going to fit a model to the data, you are going to get both all the NCL, the NCLX1, NCLX2, NCLX3, as well as the typical value, the TVCL, and also the population variability between subjects and the variance, the between subject variability, variance, as well as the inter-occasional variance. Most of the time, you don't need to use inter-occasional variability because the design of the study is not a crossover or it's not a multiple dose, or basically it's negligible. In other words, that you don't have really fluctuation of the parameter from occasion to occasion. Then don't be worried, most of the time you don't need to use that. Okay? Then again, just let me know if we have some question now or not. I don't know if nobody sent me any note, then I guess that everything is okay so far. So,
Serge, I think we do have one question.
Okay, I'm just yes. Can you cannot see the chat? Okay.
Yes, yes. Krishna, can you also go through the others and see what are the questions? So the question is from Nilesh. Okay. What if there is no sampling at different occasions?
Okay, okay. This is a very good question. I will try to rephrase that question in a different way. Suppose that first patients getting samples on first week, second week, and third week, and second patient gets sample only on first week and third week. Then he didn't get sample on week 2. It doesn't matter. The program automatically, because it's a random effect, it's just going to estimate for the population what is the inter-occasional variance globally across the population, and there's no constraint that require that you need samples and need occasion for each patient. I think that was the question. In other words, that do I need a fully balanced design that every patient got samples on each week or each occasion? And the answer is no, because it's a random effect. And anyway, even the words occasion 1, 2, or 3 can be basically swapped. It's a random effect. The first patient you can call occasion 1, the second week you can call it occasion 2, and then the third week occasion 3, or you can reverse that. It really doesn't matter. Then the answer to the question, if a patient didn't get sample on a specific occasion, the program basically is not bothered by that, because the program is looking at all the occasion when we had samples, and then it's going to estimate the overall variability within the same individual. Of course, that you need some patients that have data on different occasions. If not, you will not be able to estimate anything. If everybody got samples only in the first week, then you don't have to quantify any inter-occasion variability. Then again, the answer is you do not need to have a full balanced design with all the individual getting data on each occasion. This is not a requirement. The only thing that you will need to put in the software, it's what's the maximum number of different occasions that you have. If, for example, you follow the patient for 3 weeks every week, okay, then the maximum number of occasions is 3. But some patients maybe have only 1, some patient has only 2, and some patient have 3. A patient can have data only on week 1, another patient can have data only on week 1 and 3, so another patient can have only data on week 2 and week 3, and another patient can have data on 1, 2, 3. Okay? Any other question?
We do have several other questions, and Krishna, if you can please ask the next question in line there, please.
Okay. I cannot hear. I don't know what's.
Okay, so let me ask. Another question that I'm seeing is from Nilesh. What
Okay.
if there are, that we already asked. So the next question I see is, Srinivas, what about parallel study? We did not get interoccasion. We did not get interoccasion, right? I think he's trying to say that we will not get interoccasion if we have two parallel studies.
Now, if you have two parallel study, usually you will not have interoccasion variability unless it's unless if it's a multiple dose. If you have a multi-dose settings, and basically the patient was observed on the first dose and at steady state, okay, then it when I'm talking about crossover design, usually you change the formulation. You change the formulation from occasion to occasion, and then you can have interoccasion variability, or you can have a trend. If you have a single dose parallel study, then obviously there's no interoccasion variability to consider. Yes, but not if you have multiple doses and you observe the patient and the first dose and at steady state.
Thank you, Serge.
Welcome.
And
next.
Another question is from Sadanand. Apart from clearance, if there is consideration of volume of distribution in the equation.
Okay, I took clearance as the template parameter. In other words, I explained the concept using clearance as a template. And all what I'm telling you about clearance applied potentially to all the parameters of your model, like a volume or absorption rate or anything else. Just to simplify, I'm starting with a template parameter I call clearance because people are more familiar with the clearance. But obviously, you can have interoccasion variability in volume, you can have interoccasion variability in the absorption rate, etc. Now, once you are going to learn really the software, you are going to learn tool how to make your mind about what are the parameters that exhibit interoccasion variability. I'm just telling you in advance, and most of the time, it's only volume and clearance. And when you have more complicated model, then usually you don't have interoccasion variability for the other parameter, like peripheral volume or intercompartment clearance when you have a distribution phase or absorption rate, etc. Then most of the time it will be volume and clearance that are important to consider.
So the next question, and I think that question that Sadanand had was primarily to do with body weight. So just to clarify, and I think your question has been addressed by Dr. Gozi there. If not, you will learn more about all of this as we are actually getting into the hands-on piece of work.
Yeah, I think about body weight, I'm just going to talk about covariate analysis. That's where body weight is going to enter into the equation as an example. Then
sure.
Usually body weight is related to covariate analysis. In other words, the clearance. The clearance can be different depending on the body weight. But okay, it's a very good question in the sense that for the meantime, I talk only about random effect, which means that randomly the parameter change either between individual or within the individual. When we have a trend, then this is called the fixed effect, which means that the clearance can change with body weight. This is a trend. This is a systematic change when, for example, when the body weight increases, the clearance increases. And that's what I'm going to talk about now, which is called covariate analysis. I'm just in the middle of something. Any other question for the meantime? Then the body weight is going to answer that now. Okay. Sure.
So we do have a few other questions.
Okay.
One is how to format the data set. So Anuja, great question there. A little might be preemptive for us to address the question because we will cover all of this in our next modules. Okay.
Okay. It's a very good question, but because the format depends on the software that we are using, then I didn't want to talk about the format because I don't know exactly what format is used for the new software, RNNME. And again, Aruna, you are right. All the format issue, it's really correlated directly to the software that you're using. And the constraint for the format will be addressed later on once Tara is going to talk about the software. Obviously, they're going to take a data set as an example, and the format will come here. If I was teaching Phoenix and LME, then obviously I would talk about format. Okay?
Thank you. There are a few more questions, but I may be taking this question for now, and we will have more time to go over the questions at the end.
No problem.
So here is, if we have a rich sampling from first week and just one sample in the following week, do we model it as inter-occasion variability?
No. You can always try, but what will happen is that inter-occasional variability most of the time will work if you have enough data on each occasion. What will happen? Let me see. You can always try, okay? And I will tell you most of the time what will happen. If you have rich data on the first week and then only one sample on the week 2, most of the time the variance of the inter-occasional component will shrink to 0. Because what's happening, there's not enough information to quantify the variability within the same individual. And this is a very good question. In other words, when you design your study and you believe that you can have inter-occasional variability, you should try to be quite as much as possible balanced between occasion. Now, I told before that you don't need on each occasion information, but if you have information in 1 week, it's better to be as rich as the one that you have at the other weeks. Then again, you can try, but I can almost guarantee you that you will not be able to really find the inter-occasional variance. It will shrink to 0, because one sample, that's basically what will happen. It's not, you can do it, but I think most of the time it's a waste of time. Now, the reason to put, now I'm going to ask a question for you. You could say, okay, you know what? I have one on the first week, and then at the last week, let's say that you wait until steady state, I still have one sample. You could say, what the heck I put one sample? The idea here is that sometimes you don't know if your kinetic is linear or not linear. Linear means that when you double the dose, you double the concentration. And if you use a model that assumes that you have linear kinetic, and you have data on the first week and on the last week, you can test if basically the information that you have in the first week match the information that you have at steady state. In other words, that from the first week and the last week, you can both explain the data on the first week and on the last week with the same model that assumes linear kinetic. And if suddenly you see that on the last week, systematically, you see that the concentration is higher than expected, in other words, that you have overexposure, then most likely that you have saturation. Saturation, which means that the system is not able to eliminate the drug using a first order process, which means that the rate of elimination is proportional to that the clearance is proportional to the concentration in the plasma compartment, and then it's stuck. You have a jam, and then you have a traffic jam, and in that case, the drug level is larger than expected. Then the idea to have data on the last week is just to see if really my kinetic is linear or not. But again, if you have only 1 or 2 samples at steady state, don't even try to put inter-occasional variability. Any other question?
So, Serge, we do have a few other questions, but I think in the interest of time, we will move forward with the presentation.
Okay. You can always ask later on if you have time. Okay.
Yes, and I also wanted to just, sorry, didn't mean. Just wanted to bring up another logistics here. So you do have the option of raising your hand. So if you would like to talk, right, and want to ask a question of Serge instead of typing, you can always raise your hand, and one of us will, at the right point, would unmute you so you can ask or talk to Serge and ask the question.
Okay,
Thank
very
you.
good. Okay, then you handle that and I continue. Okay, then I really like the question because the question means that people show some interest, and I think that's very important. Always asking question means that you understand. Unlike some people that think that asking question means that you don't understand. Then it's exactly the other way around. I always say that if somebody is able to ask a question, it means that he understands 99% of the material. Then let's just talk about covariate analysis. Then again, what did we learn so far? People are different. Every patient can have a different clearance. The same patient can have the clearance fluctuating from occasion to occasion. If you want to quantify the interoccasion variability, you should have on each occasion roughly the same number of samples, quite rich data. If not, don't even try. You can have on a specific week an individual that didn't take sample at all. That's okay, no problem. Okay. Now, covariates. Covariates are very important, and let me just give you an example. If, for example, you have a male and female, and you know that male and female are different, it's possible, and you can see that's in the prescription, is that sometimes you are going to give to male a drug amount that it's large, that it's basically larger than the one that you're going to give to female. If somebody is really heavy, the weight, then maybe also is going to get an amount larger than the one that is less heavy. That's why sometimes you give the drug per kilogram. And all this is coming from the covariate analysis that we need to quantify. Then what are we talking about? Let's just look at a picture words, 1,000 words, how you say this in English. Suppose an example, you can see the weight, it's 10, 20, 30, 40, 50, 60, 70. And here just suppose that you have the concentration, which is the y-axis. It's in the log domain, very important. And then you have the time. What you can see is that you have one slope, but slope change. And what you can see is that when the weight is low, okay, then the clearance is the clearance, or if you want the elimination rate, is it's slow. You have a slow clearance, and then you can see that when the weight increase, so is basically the clearance. The drug is clearing faster. And again, I assume that everybody starts roughly at the same spot. When everybody starts at the same spot, then it means that the volume of distribution is the same, and then clearance and elimination rate play the same role. Okay. Then here, basically what we can see is that the clearance increase with weight, okay? Now, and this is called a fixed effect, and a fixed effect means that it's a trend. I see a trend that basically clearance increases weight. If I didn't have a trend, and that it was a random effect, then basically it would mean that knowing the weight doesn't give me any information about what's the clearance. However, if I have a trend, then I know that when I increase the weight, the clearance increase, and I have some kind of information about the clearance. Now, the question is that how am I going to estimate the weight effect and clearance? Now, that was the example for a continuous covariate. Now, let's just take now about categorical covariate. And suppose that you have a crossover study again, and every week the patient's taking a different formulation, same ingredient, but the formulation is different. Formulation 1, formulation 2, formulation 3. Now, I know that I'm going to confuse you because you told me, I just told you that when I had the crossover study, then I'm talking about interoccasion variability. That's right. Then what's the difference between interoccasion variability and a trend quantified by a categorical covariate? You're going to understand that very easily. You remember that last time when I talked about the interoccasional variability, I show a picture like that, is that I didn't see any trend. Same, larger clearance, lower clearance, lower clearance, larger clearance, larger clearance. No trend. Now look here at this picture, and you are going to understand that something is different. What can I see here? It is basically lower clearance, larger clearance, lower clearance, larger clearance, lower clearance, larger clearance. I exaggerate a little bit, but in average, what you can see that in average, the clearance formulation in occasion 3 is larger than the clearance formulation 2, larger than the clearance in formulation 1. Then you have a trend. Now, the beauty of the population approach is the population approach, when you do it correctly, will be able to separate what is trend and what is random. Remember that random means no trend, okay? Now, if I have really a trend, I need to quantify that trend. The same way I wanted to quantify the trend here for continuous covariate, how basically the clearance change with weight. Now, what I need to do now is to take the formula that I have so far. Remember, that's the formula that so far I built that. That's basically what I have. And now I'm going to assume to complete this equation, assuming that I can have a fixed effect, either continuous or categorical. Okay, and let's continue because that's really funny. Okay, then I have this here. Now, remember that basically this is what I have so far. Clearance is the clearance for any individual. This is the typical clearance. This is the random effect between subject. This is the random effect within subject. And again, if you don't have data that allow you to estimate that, you can cancel that. Now I want to add the effect of a continuous covariate. And let's choose the weight as the classical one with an average of, let's say, 70 kilograms. Suppose it's a normal population of adults, and suppose that the average is 70. Now I want to update the equation above to include the potential effect of the weight and clearance. And this is in orange. Usually what you do, and the program is going to do that for you, or at least, I don't know exactly what you have in the software, but at least in the Phoenix and LME, it was an option to write this automatically. When you have a continuous covariate, most likely that you want to basically to center the weight around some average. The average doesn't need to be the average of your data set. It can be anything that you want, but most of the times if adult data, you are going to use 70. Now, let's just see how it's working. The clearance depends on the weight, because you can see that the clearance, CL, is equal to the typical value multiplied by the between subject random effect, multiplied by the within subject random effect, and then I have the weight. Now, to simplify things, let's just see how it's working. Suppose that A is positive, okay? Larger than 0. Suppose that don't have between subject variability, then this cancel, it's 1. Suppose that don't have interlocution variability, then this cancel. I just have the clearance is equal to TVCL. Multiplied by weight divided by 70 exponent A. And suppose that A is equal to 1. Okay? Then what will happen if the weight is equal to 80? You are going to see, okay, that individual is going to have a clearance of, let's say that the mean is 50. TVCL is 50. Then it's 50 multiplied by 80 divided by 70 exponent 1. Then when A is positive, what will happen, and A is going to be estimated by the program, then if A is positive, it means that the clearance increase with weight. If A is negative, let's say -1 as an example, then it's exactly the other way around. When the weight increase, the clearance decrease. The program will take the weight value in the data set, because we will have a column with the weight. The program is going to read the weight for each patient, and then it's going to put this in the overall equation, and it's going to estimate A, it's going to estimate TVCL, it's going to estimate the variance of NCL, okay, the W, is going to estimate the variance, intercollision variance, if they are any. And you are going to get at the end variance for the between subject variability, variance for the within subject variability, and the power term, which is basically the A value. Then I gave you again the example. Suppose that I have a patient with a weight of 80 and there's no between subject variability and no interoccasion variability. Then you can say that this TVCL is larger than the average clearance because the A is positive. Okay, and you can see here that if the weight is less than the average, then basically this patient has a clearance that it's less than the average. Okay, then the value of the weight will determine if basically I have a clearance that it's larger or less than the average. The sign is going to tell you the trend, if it's a positive trend or a negative trend, and that's the A value. And A, it's a fixed effect because it's a value that we estimate, the program estimate, but it's not a value sample from a distribution. Remember that NCLX1 is a random effect because it's coming from a distribution. NCL, it's a random effect because it's coming from a distribution. TVCL is a fixed effect because it doesn't come from a distribution. A is a fixed effect because it doesn't come from a distribution you sample from. Okay? Then continuous covariate summary. Power model most use covariate relationship for continuous covariate, although you can use more complicated covariate relationship, but I like this kind of covariate relationship. Once you are going to work with data set, then I'm pretty sure they're going to cover all kind of covariate relationship that you can use. But that's the traditional one, the power that's centered around the mean. Okay. Now, now you could say then why should I use a covariate relationship? What will happen is that although I'm interested in the population, sometimes I want to know why the patients are different. We have two kinds of variability in the population. We have variability that we can explain, and we have variability that we cannot explain. The variability that you can explain is, for example, to tell, you know what? Male are different than female, okay? And if I'm able to use a covariate relationship that allow me to differentiate between male and female, what I'm going to see is that the variability in the population, once I account for a covariate, is going to shrink. It's going to decrease. Why? Because now a part of the population variability is explained by covariate. Let me give you an example that, let's say, an extreme case. Suppose that all the male are the same and all the female are the same. When I put them together, I see some variability because a male is different than a female. Now, if suddenly I took account the covariate relationship for clearance, for example, between male and female, then suddenly I will not have variability anymore, because I know exactly the clearance for male, I know exactly the clearance for female, and once I know the gender, basically I don't need anything anymore. Then in general, basically, the covariate relationship help us to understand the impact of the covariate on the structural parameter, and that's very, very important. If we have really correlation between covariate and PK parameter, it's going to decrease the inter-individual variability. And this is very important because think about when you go to phase 1, phase 2, phase 3, and FDA approval and all this. What's happened, what can kill the drug, even that the drug is working, is that the patient are too different. And when the patient are too different, what you are trying to do is to try to explain why they are different, and then depending, and if you can quantify the difference, you can go to the FDA and to say, okay, kids from let's say from 10 to 15 will take this kind of amount of drug per day. 15 until 30 will take a different amount, and let's say adult will take the certain amount. And when you do that, basically you are able to show that depending on the age, for example, or the weight of the individuals, you can prove that you have efficacy. While if everybody would take the same amount, or even if in some case everybody would take the amount per kilogram, sometimes you are not able to decrease the overall population variability. And what we are trying to do when we quantify the covariate relationship is to basically shrink the overall inter-individual variability. The separation of the overall population variability in what we call explained variability, again, explained by the covariate, we want to differentiate between that and the unexplained variability not explained by the covariate. Okay, that's why we do a covariate relationship. And understanding and quantifying the impact of covariate is critical to optimal drug dosing. Then if you have the ability to design, basically for labeling purpose, if you are able to change the dosing depending on some covariate, if it's a law, then and you can see that it makes a difference, then that the difference could be between the drug accepted or not accepted, or even better case is that you are going to decide that the drug will be given only to adults, because when you take adults and kids, you are not able to find the right dose that will apply to the whole population, even when you try to use covariate analysis. Then that's one of the reasons we do covariate analysis. Now, that was continuous covariate, and now what I did then again, remember what we work here. Clearance is the individual clearance. TVCA is the typical clearance. NCL is a sample from a distribution that quantifies the inter-individual variability. NCL X1, 2, and 3 is a sample from a distribution that quantifies the inter-occasional variability on each occasion. The continuous effect, the continuous covariate effect, here weight and clearance, is quantified by this kind of equation. And now what we need to do, suppose that we have two categorical covariates. A categorical covariate called gender, and let's assume that for gender we have two categories, 0 and 1. Let's say 1 for female and 0 for male. Okay. And suppose also that we have a disease status that has 4 categories, 0, 1, 2, and 3. For example, it could be a drug where the clearance depends, for example, and some category covariate that can have 4 categories. For example, just an example, level of cholesterol that you put in category, normal, little bit high, high, and very high, just an example. Then you could take the cholesterol level at baseline and put this in category, and then suppose that clearance depends on the category, the cholesterol category, then you could have an effect. Now, one thing that's very important, which is called basically degree of freedom. If you have gender, which has 2 categories, you need only to multiply what you had before by only 1 term, not 2. And usually you take the second value for gender equal 1, and I'm going to show you why later on, okay? Then now I multiply, and that's basically the gender effect. And I multiply by exponent, and the reason to put an exponent is to make sure that whatever is a gender, which is a parameter, that the program is going to estimate, but that applied only when gender is equal to 1. Again, that's an index. Remember that we talked about the index? Then gender equal 1 is equal to 1 only when gender equal 1. Now let me give you an example, and that the next slide is going to show us an example. Suppose that I don't have inter-individual variability. Suppose that I don't have inter-occasion variability, and suppose that the weight is 70. Then what I'm left with, TVCL multiplied by the green box, okay? And forget about the disease status. Suppose that I'm taking a female, gender equal 1, and suppose that A gender equal 1, okay? Then if the program is going to estimate A gender and it's equal to 1, and I'm talking about the female, what will be the clearance for that female? No random effect here, no random effect here. The weight is 70 kilograms. Then the clearance is equal to the average clearance multiplied by exponent 1. That's it. In other words, when A gender is positive, what you can see is that the female has a larger clearance. Suppose now that we are talking a male, okay? And again, A gender is equal to 1 because it's the same for the whole population. It's a fixed effect, it's 1 value. Then what will happen for the male? Male gender equals 0. Then gender equal not 1. Then gender equal 1 is 0 because gender equals 0. Then this is 0. This is 0. Then whatever you want multiplied by 0 is 0. Exponent 0 is 1. And then the male will have a clearance of just the typical value. And when you write this equation, which is basically what I explained you. Suppose no random effect with 70, gender equals 0, disease status equals 0. That I explain now what happened with the disease status. I explain you basically the green box. Now you can apply exactly the same thing for disease status at 4 levels. But what is more important that I didn't answer to the question that maybe you didn't ask, gender has 2 values, but I see only 1 multiplication. The reason is that I have 1 degree of freedom. Because when gender equals 0, all this cancel, and the male will take the value of TVCL multiplied by this if it exists, multiplied by this, and multiplied by the weight effect. Then in general, if you have n category, you just need n minus 1 multiplication. If you don't do that, you will have what is called, your system will be basically over parameterized because you add something that is not needed, which is a problem. Now let's just take about the second covariate. The disease status can be 0, 1, 2, and 3. And suppose that no random effect between, no random effect within, the weight is 70, the gender is equal to 0. Then the green box disappear, the orange box, and the weight is 70, then the orange box disappear. No between, the blue box disappear, the exponent NCL disappear, you are just left with the TVCL. Suppose that the disease status equal to 0. Then this disappear, and this disappear. And then basically the clearance for that individual will be the typical clearance. Suppose that the disease status equal 1, okay, and no random effect, and the weight is equal to 70, and it's a male. Then again you are left with TVCL. Now the disease status equal to 1, then disease status 2 and 3 disappear, and you are left with disease status equal 1, which is a 1, and the B1 will define basically the effect of the disease status when the disease status is equal to 1. The program is going to estimate B1, B2, and B3, and is going to read for each patient what are the disease status. Then most of the time, the disease status is the baseline disease status, which is a time-independent covariate, which means that the covariate doesn't change with time within the same individual. Then that was basically the summary of all what we did so far. What did we learn so far? And then after I will let you ask some questions. Fixed effect define the central tendency of the structural parameter. All what I said about clearance applied for any of other parameters. Okay, the fixed effect can be modified by incorporate covariate relationship that can be either continuous or categorical. Individual random effects are always normally distributed, while the inter-individual variability for the structural matrix can be of any distribution shape depending on the transformation used. We differentiate between inter-individual random effects that occur at the individual level, okay, which means that from individual to individual, you sample another value, and inter-occasion random effect that occur at the occasion level. What does that mean, that occur at the occasion level? It's that from occasion to occasion, you sample another value, the NCLX1, NCLX2, NCLX3, as I mentioned here. Then we have the fixed effect, which is the weight effect. We have, which is a continuous covariate, and then you have the categorical covariate that can have two categories. In that case, you have only one multiplication, or more than two categories, and you have, if you have n category, you are going to have n minus 1 multiplication. In general, I'm taking always the large category in my equation, but again, it's completely arbitrary. As long as you put three multiplication with different category, that's okay. You have the choice, okay? That's not really a problem. Then I will stop again here before going to the last part for this first workshop. In the next workshop, we are going to talk about something more complicated, which is a categorical response, PKPD, time to event, count data. Hopefully I will have time to talk about all that. That's quite more advanced, but let's just stop now. If somebody, Aruna, you can tell me if you have more questions, I will be happy at least to try to answer.
Sure. So we have a question again. I'm not going in an order here.
Okay.
One of the questions from Nilesh is, weight generally affect both clearance and VSS. Do we calculate different values for both?
For what both? For both what?
So again, let me try to, I'm trying to read the question as is, but might be, I will, Nilesh, if you raise your hand, maybe I can unmute you so you can ask the question. Let me see if I can find you here.
He raised a hand.
Oh, he did? Okay, let me see. Yes, okay, let me unmute you here. Okay, I think I have asked to unmute you. Did
Okay.
I? Yes, you are unmuted, Nilesh. Go ahead, ask the question.
Yeah, so Serge, I would like to ask that weight generally affect both clearance and VSS, and in the covariate analysis, we generally use the A as an exponent. So do we calculate that exponent differently for both the parameters?
Yeah, basically, first it's not really VSS, but it's more the volume distribution. You know, VSS is coming from the non-compartment analysis, and when you do modeling, then the parameter that you are going to have for one compartment model will be volume and clearance. Okay. Now, as I mentioned, the equation that you see here applied for any of the parameter. Then, if you have volume and clearance, you can just swap the word CL by the word volume, and the A will be applied for the volume, which means if that's your question, is that it's possible that the clearance, for example, will increase with weight and with a certain speed, and the A value, let's say 1, let's say 0.75, that's usually what's happening. And then when you do the same thing with the volume, you can see that the A for the volume is, let's say, 1. In other words, the program is going to estimate different power terms for different for different PK parameters. Now, if you are going to have that's special techniques that I will not cover here. Again, just an introduction. That's certain techniques that allow you to find also what are the most important covariates that you should put in your model, and it's possible that when you are going to have some practical aspect taught, then it will be you are going to touch this kind of problem. But to answer to your question, each parameter can be tested separately, and each can have their own separate power term. Or for example, clearance can depend on weight, and let's say peripheral volume will not depend on weight or something like that. Okay, does that answer your question? Again, I used clearance just as an example, but all what I'm telling you about clearance applied to any of the other one. For example, clearance can have, for example, between subject variability, okay? But bioavailability, for example, maybe can be the same for each individual. Then you will not have between subject random effect, neither within subject random effect. And maybe bioavailability doesn't depend on weight, then A is equal to 0. And doesn't depend on the gender, then A gender is equal to 0. Okay? Then everything.
One more point. This A value, can we fix it, or should we? Generally, I have seen that people use allometric scaling exponent factor and fix that value. Should we estimate that or fix it?
Okay, very good question. It depends if you have enough information in your data to estimate it. Usually when you do allometric scaling, which means that you want to go from animal to human or something like that, it's very difficult from the data that you have to estimate the A. And then usually if you give the dose not per kilogram, then most of the time you're going to use an A of 0.75 for clearance and an A of 1 for volume. If you use the dose, that's very important. If the dose is normalized per kilogram, then for clearance, you are going to use minus 0.25, which is basically 0.75 minus 1. And for volume, you are going to use A of 0, which is 1 minus 1. If you have a lot of data for different species, then you can try to estimate. Now, if you have only human data, then you are not going to fix the A, because now really, and you have a population with a population and patient have from weight from 50 to 120 kilograms. Then in that case, you should not fix the A because it's not an allometric scaling. Allometric scaling refer usually for interspecies extrapolation. Okay.
Okay. Yeah.
But again,
Thank
the program, at least the NLME program, allow you either to fix the A or to estimate the A. And again, it's your decision to do that. I would never estimate, I would never freeze an A if I have human data and I want to know what's the weight effect. Because if I want to know what's the weight effect, then why should I fix it? I want to check if there is one. Allometric scaling is a different story because most of the time you say, okay, I have data in mice, for example, and I just want to estimate what will happen in human, my first guess. Then you don't have the human data. Then in that case, you cannot really estimate the Allometric scaling factor. Okay?
Okay. Yeah. Thank you.
You're welcome. Any other question?
So we do have many other questions up here in the chat.
Okay, we can ask more because I think that I need something like 15 minutes. I will finish just the error model and that's it for today.
Sure. So again, I would encourage the participants to raise their hand if they want to ask a question of Serge. And in the meantime, I will actually go back to the chat and ask another question. So there is one question which is, what is the effect of number of covariates on the sample size?
I think that the question should be, how do you say? And the sample size for what?
So I think this is what I'm reading, and I could be wrong. But what I'm reading is how many covariates. I mean, I think they're trying to understand. We always talk about that your covariates and sample size should have a certain proportion, in the sense when you have a large sample size, you have the ability to have more covariates tested. So I guess this is what I am understanding from this question. Again, Nusrat, if you would like to come on and ask the question of Serge, yeah, there you raise your hand so I can unmute you and I can also put you on video.
Okay,
so please,
raise hand, I see.
Yeah, please accept as I ask you to. Yes, now you have, and you can also come on video if you would like.
Yeah, so Aruna, I am okay with the audio being there. Yeah, I think you got my point correctly, that I just wanted to know how many covariates, I mean, what would be an appropriate sample size? I mean, data sets would be for considering number of covariates that you can accommodate and you can assess properly. So,
okay, yeah, I understand the question. To tell you the truth, there's no really straight answer to that because it depends on the sensitivity of your system. I will explain you the strategy rather than to answer the question about sample size, because there's no straight answer about the sample size. The first thing that you need to do when you do covariate analysis is just to talk with the expert that will tell you what are the relevant covariates to even put in the equation when try to assess the covariate relationship. That's the first thing. And I would not think about more than 5 to maximum 10 covariates, independently of the sample size, okay? Independent of the sample size. There's an algorithm called a backward automatic covariate search. It's an algorithm that is going to take one covariate at a time, doing the forward step, and it's going to see if basically what is the covariate that is the most significant. And again, you select only the covariates that are relevant based on the pharmacology and based on the knowledge of the expert. That's very important. I don't want you at the end of the day, you are going to say that clearly depends on the color of your eyes. Okay, that's basically what I mean. When you are done with all the covariates, and again, you can have many covariates, I will not take more than 10, independently of the sample size. Then the program, what the program is going to do is going to go to the next step, which is the backward step, and is going to tell you at the end of the day what's the most significant covariate. The sample size enter into account when you are talking about power. And again, you can apply the same strategy for any sample size, but in practice, when the sample size is very small, what will happen is that the probability to detect a significant covariate is decreased with the sample size, when the sample size decreases. Then the answer to your question, there's no straight answer about if there's a direct relationship about how many covariates should I use when I have a sample size of 10, 20, or 30. There's no straight answer, because a sample of 10 patients can have 10 patients with rich data. In that case, maybe we'll be able to detect a lot of covariate relationship if we have covariate relationship. But you have the same 10 patients, very sparse data, then maybe I'm not going to detect anything. No. To answer to question a little bit more deeply, not be able to detect covariate doesn't mean that you don't have a covariate relationship. It just means that you don't have the power to be able to detect a relationship because of the sample size. But again, there's no straight answer. For example, sample size of 30, you can go up to 5 covariate. Sample size of 100, you can go with 20 covariate. This is not correct, because it depends on the sparse versus rich sampling. It depends on your data. It depends on the true effect of the covariate. For example, if you have a very small effect of weight, okay, then you will need really a bigger sample size to be able to detect it. But I cannot tell you in advance how much, because it depends on so many things that there's no straight answer to that. Okay?
Arun, can I request you to ask the next questions on the chat, please?
Sure. Hi, Serge. I would like to take up the questions from the previous Q&A, which we missed. So, which is about the variability part. So we have Ravisha. His question states, we have a clinical study done at 2 different time points or at different places, and the samples were analyzed by different labs with different bioanalytical methodologies. So, and in this scenario, there might be errors due to the variation in different labs. And if it is not a crossover study, in such a scenario, can we consider the inter-occasion variability?
Can you repeat the question? I want to make sure if I understood correctly. Yeah. You're talking about basically observations that were recorded in different assays, different labs?
Yeah, exactly. So in such a scenario, can we consider the inter-occasional variability?
No, this is not inter-occasional variability. It's related to the next step that I'm going to talk about, which is the error model. What you are talking about is the observation, if I understand correctly. You have different labs, and each lab has a different assay, okay? And then different assays, some assay can be more precise than other. And it will affect another kind of random effect, which is the random effect of your observation itself, which is the next step. This is not inter-occasion variability. Inter-occasion variability, or it's not inter-occasion variability, because we're not talking about the clearance that's going to change from occasion to occasion because there was a different lab. Unless really the lab has a bias. And again, I assume that there's no bias. Usually a good lab can have different assay precision, okay? And the assay precision is going just to tell you how precise will be my observation that I'm going to record. And then if you have different lab and different occasion, then sometimes you should model the error model. And that's what I'm going to talk now. That's why I should stop here. And just we are talking about the error model that can be different because the precision is different across the different labs. Okay, but it's definitely not inter-occasion variability. But it's still a random effect. But again, that's the next step. For the meantime, I talked only about parameters. I didn't talk yet about the response. And what he or she talking about now, it's basically the precision of assay that can affect and that we should account for it. Okay, and that's the next step. That's the error model.
Thanks,
okay.
Sir. That answers the question. So we have a next question from Nusrat. So how does the program treat intra-occasion variability if the factors affecting clearance are actually changing rapidly, something like a case with a patient in sepsis.
Okay. I think that we should distinguish between random effect and fixed effect. Again, tell me if I'm wrong. What sometimes can happen is that you can have a trend that for some reason, you can have two examples. Again, I'm not sure that answers the question, but let me explain what can happen. We should differentiate between a random effect and a fixed effect. If for some reason the clearance change from occasion to occasion for each patient, but in the same direction, which is maybe what you are talking about now, depending on some patient characteristic, then basically the clearance change. This is a fixed effect because you can pinpoint and tell why the clearance change. When you don't know why the clearance change, it's called the random effect, and then you should imply basically the intra-subject, inter-occasion variability. Now the next question is to say, how can I differentiate between both, right? The program, suppose, let me give you an example. Suppose you have 3 different occasions, okay? And then you look at you see my screen, yes? You see the NCLX1, NCLX2, and NCLX3. If it's really random, then what we are going to see is that sometimes NCLX1 is positive, this one is near 0, this one is negative, and then it can swap. Then the next patient, this one is positive, this one is negative, this is 0, this one is positive, positive, this, you do not see a trend. If you test inter-occasion variability and you see that systematically, you see that NCLX1 is positive, NCLX2 is almost 0, and then NCLX3 is completely negative, then apparently you messed up. And what you have, it's not inter-occasion variability, but it's really a trend, which is what could happen if the clearance change with time, for example. But the clearance change with time, it's information, it's a trend. In that case, you should model that trend and put in your equation the clearance change with time. And again, how to do it, that really will be once you are going to do practical examples. But again, to answer to your questions, if for some reason the clearance change, the word for some reason means that it's information, it's not random. You should use inter-occasion variability only when you don't know why the clearance fluctuates from occasion to occasion. Okay? Next question.
Thanks, Serge. Yeah, we have one question from Vishal. So with regards to the disease status, how does the program estimate the values B1, B2, and B3?
Okay. Okay. You asked a tough question because now we have to go back. What's basically what the program is doing? Let me explain you in simple terms. Again, later on, next time I'm going to talk about the likelihood. But let's say that I didn't have any algorithm. Okay, the program is going to take each individual and suppose that it's going for a patient is going to start with a certain value for TVCL, and the program again is going to try specific value for NCL, for NCLX1, NCLX2, NCLX3, and A gender, and B1 and B2. That's just an example. You take all this value and then it's getting the clearance. It's doing the same for volume, okay? And if it's a one compartment, it's getting the predicted concentration, okay? Now, you look at the predicted concentration, and then now you look at the observed concentration. Then he's looking at the same patient, all the samples that you get at each time. The program can compute what is called the likelihood, which is proportional to the probability. What is the probability that basically the TVCL that I told you, the NCL told you, the NCLX1, X2, and X3, the A and the B1, B2, and B3 explain the data for that individual. And then you go to the next individual, etc. Then the program is going to use a special technique. It's going to start with an average TVCL. That basically again, once you are going to have a data set, they will explain you how to do that. You start with, let's say, TVCL equal 50. You start with the inter-individual variability, let's say, with a variance of 1. And same for the inter-equation variability. You always start with an A of 0, which means that at the beginning you say, suppose that I don't have an effect. You start with a B1 of 0. And to answer to your question, the program is going to test. It's going, okay, if I'm changing B1, B2, and B3, is my likelihood improving? Improving means that the likelihood is larger. Or if you want the log likelihood is larger, or if you want the minus log likelihood is smaller. The program is going to minimize what is called the -2 log likelihood. And the -2 log likelihood, the best one, will be associated to a specific value of B1, B2, and B3. How does it work? This is basically completely quickly outside the scope. But the idea is that you have what is called an objective function that you minimize. The objective function is the -2 log likelihood. The program is taking all the patient, all the data, all the observation, and then using a specific algorithm, test the value of B1, B2, B3, A, TVCL, and all the distribution. And at the end, it's going to give you back the answer. Now, of course, once you are going to work on a real data set, there are cookbook. By the way, I wrote a full cookbook, a big full book, cookbook that explains you how to start from scratch. Basically, there's a cookbook that I made available for many people that explain how you can basically slowly but surely find what is called the optimal model. And at the end of the day, you are going to see that basically there's no disease status effects, or that there's disease status effect, but there's no weather effect, or there is inter-individual variability, but there's no inter-occasion variability. And all this can be done step by step. Okay. But to answer to your question, everything is related to what is called the likelihood, or the minus log likelihood, -2 log likelihood more exactly, that you are going to minimize. The minimum will give you the value of B1, B2, B3, A, and all the variance and the fixed effect that basically give you the minimum value for the -2 log likelihood. Next question.
Thanks, Serge, for the clear explanation. So those are the questions for this session. Maybe we can continue with your presentation.
Okay. Because some of the question you ask, I mean, or your colleague ask, is related to the next step, which is basically the. Okay, this is all what we learned so far, and now let's just talk about the response rate. I talked so far only about the parameters, but who cares about the parameter? At the end of the day, you use the parameter because the parameters are linked to a model. Now, let's just take, again, that's exactly what we learned so far. And now let's just take the simple examples. We have volume, we have clearance. And again, I have the equation for clearance and I have the equation for basically the volume. Now, be careful because the A here, it's not the A here. In other words, every parameter will have their own power terms and their own and so on, etc. Then this should not be A. I mean, that's A for CL and that's A for V. It's same thing for A. You see, I put A gender and I put A gender V. Okay. Then the A can be different. Most likely will be different. Okay. Then I have an equation for the clearance. I have an equation for the volume. And suppose that I know the dose and I know the time, then if I knew for each patient their clearance and their volume, I would be able to find the clearance, the concentration. Now, what is an observation? And what's the link between an observation and a predicted concentration? In order to understand that, let's just make an hypothetical experiment that it's impossible to do in practice. Let's just take one patient, okay? You follow me? And let's just take one patient and let's just record an observation at time equal 1, t equal 1. And suppose that I'm getting a concentration of 59 nanogram per liter. Suppose now that I was able to take the same patient, assuming that it doesn't change, that the clearance doesn't change or nothing is changed. The only thing that can change is the assay. And now let's say that the next time, instead of 55, I'm getting, let's say 52. Then I'm doing the same thing again. Again, I cannot do this in practice because I cannot take the same patient at the same time many times. Let's suppose that in theory I could do that. If I was able to take the same patient and let's say 1 million times to record this observation, what I would see is that basically I will get a distribution. I will get 52, 55, 58, 60, 48, 61, and let's say that I have just 1,000 value. Then basically what I will see is that I will have a distribution which is called the distribution of my observation. Because my observation is characterized by distribution, my observation is itself a random effect. In other words, in practice, I will not get 1,000 value from the same patient at the same time. I will get only one value, the 55. Then this 55 is a sample from a distribution that if I would have 10,000 value for that time for the same patient, what I would see is that the average, the mean of that distribution will be exactly my best guess about the true predicted concentration for that patient. Then now what we can write is that basically the observation I'm getting, which is a sample from a distribution, as a mean, which is the predicted concentration. And the difference between the predicted concentration and my observation, it's called epsilon, which is a random sample from a distribution that is normally distributed for continuous response with a mean of 0 and a standard deviation of SD. The program is going to estimate that standard deviation, but we can have two different scenarios or even three different scenarios. Suppose that you have an assay, and most of the time an assay at a lower concentration, there's less noise in the data. And when the concentration increases, you have more noise. In that case, we say that the standard deviation is proportional to the predicted concentration. And again, if I was doing a hypothetical experiment, what I would see is that at two different times when the concentration is low and the concentration is high, I can see that the standard deviation is going from 5.5 as an average of 5.5 and standard deviation 0.55. And suppose that when the concentration is higher, then I'm getting an average of 55, but so is the standard deviation multiplied by 10 also. When the standard deviation that characterizes the randomness of your observation that you record, if you see that the standard deviation is proportional to the true predicted concentration, we say that we have a multiplicative error. If you have a multiplicative error, the program will estimate what is called the CV, the coefficient of variation. Most of the time for assay, for good assay, it's 5, 10, 15%. When you have a big precision issue with the assay, or your model is not correct, which induces a bias, you are going to get a CV that's really larger than 15 or 30%. And then maybe you should think either about your model that's not correct or something happened with the assay. Well, I don't know what can happen. Then we can have three different scenarios. Most of the PK models will assume either a multiplicative error, which means that the noise increases proportionally with the predicted concentration. Sometimes when you have very low concentration, we have basically the effect of the limit of quantification, which means that even if you have a very low concentration, you still have a big error relative to the concentration level itself. And then we have what is called combination of additive and multiplicative error. And the program is going to estimate the standard deviation for the additive component of your error model, and also the CV for the multiplicative component. And again, when you are going to practice with example, you are going to differentiate between the two cases. When you have pharmacodynamic data, then usually the pharmacodynamic data, they spend across a quite small range of values. You know, unlike PK that you can have different dose and the concentration can go from 0.1 to 10,000, which is a huge range, then obviously proportional error is more is the one to consider. When you have PD data that go, let's say, from 10 to 50 as an example, then most of the time you can assume that the variance of your observation doesn't change doesn't change with the predicted response. In that case, would be the PD response, and then use an additive model. Then I would like to stop here because it's almost 6 o'clock. I would like just to tell you what I'm going to do at the next session. I'm going to introduce you to the likelihood function, then to go to the pharmacodynamic turnover processes, steady state versus non-steady state condition, indirect response model, and then mathematical equation for indirect response model, and then effect compartment. And then I'm going to talk about categorical response, then count data, and then time to event. I hope I will have time to talk about all that because it's a lot of material. Then I think that we are done for today unless we have more questions. I will be happy to answer any of the questions. Also, I don't know how you can arrange that, Arun. I will be happy to help any students if they can send me an email. And maybe a part of my responsibility will be to try to help if I can there. But again, this is just an introduction. Obviously, you need to practice, and because the software is not the software that I know. I mean, I know just you know, Phoenix, non-mem, monoliths, and all this. Then I just wanted to introduce the students to this important concept. Hopefully it was successful. Okay.
Thank you so much, Serge. Really appreciate you taking the time and walking the students through the introduction of pharmacometrics here. And again, this is just the, I would say, tip of the iceberg. There is a lot more that you would be learning in the next 3 months to go. And in fact, again, I would like to apologize for all the delays that we have had in terms of the technical difficulties and me losing my internet connection. And thank you for being gracious here, Serge. We did not get a chance to formally introduce you before we started today's workshop. And I would like to invite Anna Hendricks from Certara to introduce Serge. But before we actually get to that, Serge, if you can stop sharing your screen, maybe I can just quickly share the screen and say a few words here regarding our sponsors. All right, so just to, let me actually bring you to the main introduction of the workshop. Again, we are trying to go backwards here, but just wanted to give you an idea of the various topics that would be covered, and also wanted to share a few things from our sponsors. So again, as you know, this workshop is hosted by Project Dontabhaktuni, and the workshop is actually sponsored by Certara. And we have our sponsors also present here on the call with us. That is Anna, Keith. I hope, Rajan, you're also back online. So I would like to take a couple minutes for us to go around to make sure that we have all of them here. And Arun, if you can please unmute and put Anna on video, she can introduce Serge.
Yes, hello everybody. Can you hear me okay?
Yes, thank you, Anna.
Excellent. This is Anna Henry from Certara, and I really want to thank Dr. Guzzi for this very, very informative lecture today. Dr. Guzzi has extensive experience in the pharmaceutical industry. He's a known expert in the PK/PD area. He is an affiliate professor at many universities around the world, and won't name all of them, but you can read it in his bio. And he has authored many peer-reviewed publications and presented over more than 30 workshops. I have had the pleasure to work with him for many years, and it's great to have him in this workshop again. Just really want to thank again Dr. Guzzi for being here with us today. Thank you.
Thank you very much. Thank you very much.
Thank you, Anna. So as you all know, this is the module 1. Today was the day 1 of the module 1. And from now on till August 27th, my request is that we have provided you the details of the course and the various workshops that will happen. So every Friday, these 2 hours, please block your calendar. So the next steps from here would be that you have already received Dr. Guzzi's presentation and the homework assignments. These homework assignments, we would encourage for you to start working on them right away. Next Friday, you will be meeting, and all the participants in the workshop have been divided into teams. And these teams are led by team leaders who have been carefully chosen, who have some past experience with Pharmacometrics, and would be supporting you, would be working with you on a one-on-one basis if needed to ensure that you can get these concepts well. Another thing that also would be happening is that we will share your contact details with your team leaders, and they will be in touch with you throughout the week. So next week at the same time, you would be meeting to go over the homework assignments, and Dr. Guzzi would be here depending on his schedule, maybe for an hour or so to help address any questions that you have. And then we would again have on July 9th, another 2-hour lecture by Dr. Guzzi, where you will get to, where he would actually bring your understanding to the next level. And following that, again, you will have the homework assignments and stuff that you'll be working on. Again, I don't want to get into the nitty-gritty and detail of it. You can actually find that in the course flyer. And the same would be the case with module 2. Again, Arun, if you can unmute Dr. Rajan and maybe also bring him on video if that's a possibility. Maybe he can share a few words about his module.
Good evening, everyone, and thank Aruna and team for giving me this opportunity. So my module, it's kind of the first one. Guzzi is covering all these basic fundamental concepts of pharmacometrics, bringing you up to the speed for understanding the concepts. And I will be giving kind of orientation on R. It will be very fundamental at the fundamental level. And I think that is good enough to start moving towards the RS and LME, that actually the program to work on these models, right? So for the 2 weeks, we will have my sessions, and I have a lot of homework assignments which you can do. Such Guzzi would have given definitely theoretical based homework. I have a lot of homework to make you work in R. And definitely we can meet and discuss and make sure that everybody has a hang on how to work with R. Once you are ready with that, then I think Keith will take over and show you around how to do modeling, whatever the concepts we are doing, that is in R. Thanks for the opportunity, Aruna. Thanks for everyone.
So Arun, if you can please have Keith unmuted and also on video, I would appreciate that.
Hello, everyone. Thank you, Serge. That was an excellent introduction of some of the fundamental concepts, and I was pleased with the thoughtful questions from the audience. So yes, I'm very much looking forward to presenting R-Speaks NLME, which I think will very nicely tie together Serge's talk as well as Dr. Malayaswani talk. So great. Looking forward to the course.
Thank you, Keith. Thank you. So I actually also want to let you know that in the next couple of days, you will get access to the RSNLME tool. We would encourage you to start familiarizing yourself with the tool, so you will have the access of that tool for the 3 months during the workshop and also 3 months after the workshop, and really acknowledge and appreciate Certara for giving you the access to this tool for being a participant in this workshop. So do take advantage of that, and we would, again, Dr. Keith is here to help you with questions. It may be a little early because you're not introduced to it, but if you have used other tools in the past, I think this should be a pretty seamless transition. So moving on to acknowledgements. Again, a workshop of this size would not have been possible without the endless contribution and support. I'm really happy and excited to say that our team, in terms of the volunteers who have participated to make this workshop possible, has expanded quite a bit. Thank you all for all your contributions. And I will actually be talking more about each and every individual as we are coming through the various modes of this workshop. And again, I also acknowledge and appreciate all of you who have stepped up into your leadership roles and accepted our invitation to become team leaders and take on leading your teams and helping with the homework assignments. So please stand by. Again, I know some of you have had some technical issues in terms of maybe not getting emails. Some of you have had some other technical issues that you want to reach us for. So me and the rest of our volunteer team will be here online to talk to you one-on-one. At this point, I think we are the workshop for today has ended. However, as I said, if you would like to reach us, talk to us, we are here. We will take down all your concerns and questions and make sure that you have you receive all that you're looking for. So thank you all for being here, and thank you, Serge, for walking us through the introduction to Pharmacometrics today.
Pleasure.